Okay. I am writing again the two relationships for the two waveform of models that in the integral form that we have seen so far. The first one is the linear reservoir, or maybe better, the first one is the time area method. And the relationship is written in this way: Q star is equal to the integral between 0 and T star of precipitation at time T star minus tau multiplied by 1 over A the A tau the tau integral extended over the tau. And the second is the linear reservoir and the relationship is written, as you remember, in this way: Qt is equal to the integral between 0 and T star of precipitation T star minus tau, which multiplies 1 over k A E, sorry, to the power of minus T tau over A the tau. And by writing in this way, I am neglecting the depletion term Q0 times E to the power of minus T over K. So let's assume that we continue to neglect the depletion term just for simplicity. And yesterday I already pointed your attention to the fact that these two relationships are very similar. And in fact, we can write these two relationships in a general form, which includes both. And the general form can be written in this way: Q of T star is equal to the integral between 0 and T star of, again, precipitation T star minus tau. And because so far the two relationships are the same, are identical. And I can write this term, which is different. It's 1 over A day A over T for the time area method, 1 over K E to the power of minus tau over K for the linear reservoir. I can write it in a general form, which is, I can use the symbol H of tau in the tau, where H, again, for the time area method is 1 over A derivative of A tau over time, and for the linear reservoir, H takes the form 1 over K E to the power of minus tau over K. If I use this relationship, this general form, then I can use just one relationship for both models. And this model, if I write the general relationship in this way, this model takes the name of generalized linear model. Generalized, of course, the meaning is obvious, it's general. Linear, because in fact, these two models are linear, meaning that river flow is computed as a linear function of rainfall. If you look here, in both cases, you have that river flow is computed through by multiplying rainfall for a series of coefficients that depend in one case by the area curve, time area curve, and in the second case depend on k. But the form is, in any case, linear, the form of the relationship. How do we define a linear relationship? A linear relationship is such that a function f is linear if f a times x is equal to a f of x. This is the first condition. These are linearity conditions. And the second condition is f a plus x is equal of f a plus f x. This is just the definition of linear function, and you can recognize, we could prove it, but I don't want to go too much into the details. We can prove that the generalized linear model is indeed linear. And what is important to note for a linear model is that the superposition principle is valid. Okay? I think it is the correct terminology, superposition. It's the principio di sovrapposizione degli effetti, meaning that, in practice, if you have two rainfalls, look at this condition here. If you have a function of two terms, you can obtain the result by summing the effect due to each individual term. It means that if I have a rainfall that takes the value, for instance, of 20, I can compute the river discharge originated by a rainfall of 20 by summing the river discharge given by a rainfall of 15 plus the river discharge given by a rainfall of 5. This is the practical meaning of the superposition principle. And in hydrology, in general, this is not true, because we well know that there are some limiting values for rainfall that do not originate any discharge. So we know that if it rains, the first part of the rainfall infiltrates completely in the soil, so doesn't give any river discharge. And there is a threshold after which we start observing some river discharge, meaning that the superposition principle is not valid, because if you have, say, a rainfall of 10 and 10 is higher than the threshold to see river discharge, then you see some water in the river. Let's suppose that the threshold is 7, but you can't say that the effect given due to the rainfall that takes the value of 10 is due to the sum of the two effects due to rainfall of 5, for instance, because for a rainfall of 5 you don't have any water in the river. If the threshold is 7, it means that if it rains 5, you don't see any water in the river. So the sum of two 5s is just 0. Why? The river discharge for a rainfall of 10 is different than 0, is positive, because 10 is exceeding the threshold. In general, when you have processes that are characterized by thresholds solely, then these processes are nonlinear. So in general, hydrology is nonlinear, and I would say highly nonlinear. But nevertheless, it can be approximated with linear models. And the reason why we use this approximation is simplicity, of course. So we can use these linear models, but we have to be aware that they provide a schematization of nature, of the natural process, which is not reliable in the strict sense. It can be reliable enough, but it's not perfect. Anyway, these are linear models, and this is a generalized linear model. The literature proposes many different alternatives for the form of H tau. We have seen 2 of them, but there are many more. If you browse the literature, you find many more alternatives, and even if you Google, you find many more alternatives. The name of this term is called in the English literature, is called with the acronym is IUH, which means instantaneous unit hydrograph. Why instantaneous unit hydrograph? Because H, from a physical point of view, is the response of the system, the response of the river, of the catchment, let's say, to a unit rainfall which is instantaneous. If you look at the meaning of H is multiplied by rainfall to obtain river discharge. It means that if you take just H is the discharge given by a unit rainfall which is instantaneous. It's a Dirac function. If you assume that rainfall is given by a Dirac function, then you get a river discharge that is given by H. This is from a physical point of view. Let's suppose that you have over your catchment a unit rainfall which is poof, instantaneous. And then you get the response given by H. By the model. This is the model, okay? It's not the real system. This is the model. Because of course, on the real system, if you give a unit rainfall, maybe it's not enough to trigger river discharge. Maybe that is below that threshold of infiltration and you don't see anything. But according to the model, H is the result of a unit rainfall instantaneous. And therefore the name instantaneous unit hydrograph. Again, if you Google for IUH and hydrology maybe to refine the search, you find different alternatives, several alternatives for the instantaneous unit hydrograph. Of course, each alternative is characterized by particular behaviors, like the linear reservoir is adapted, as I said, it's suggested when you want to model catchments that can store a lot of water, where storage is important. Instead, if you use the time area method, then you assume that storage is not much important. It's just transfer of mass that is important. And so I said the time area method is good for steep catchments that do not store much water, while the linear reservoir is good for flat catchment that store a lot of water. And there are more alternatives characterized by one or more parameters. In this case, for the linear reservoir, the parameter is K. For the time area method, the parameter is not defined in this form because the unit hydrograph is just given by the shape of the time area relationship. But if you assume that the time area relationship is linear, then you get just one parameter even here, which is the slope of the time area relationship. This is not much important. I don't want to go into the details. What is important to note is that the number of parameters is not fixed. Different models can have different number of parameters. One for the linear reservoir, maybe more than one for the time area method. Other models have several parameters. One thing that I didn't say explicitly, or maybe that I didn't put in enough evidence maybe, is that, keep in mind, P is rainfall intensity density multiplied by the catchment area, and I said this clearly yesterday. So it's like a flux of rainfall, but also I probably didn't emphasize enough that this is effective rainfall, meaning that do you remember the coefficient C of the rational formula, and that takes into account that some rainfall is lost, okay? And therefore we distinguish between gross rainfall, which is pioggia lorda in Italian, and net rainfall or effective rainfall, which is pioggia netta in Italian. You already know the difference between the two, because you studied it in hydrology. The difference is just that the gross rainfall is just the rainfall that you measure if you put a tank outside, and it's the rainfall that you observe. The effective rainfall is given by gross rainfall minus rainfall that is lost for evaporation, deep infiltration, other processes. It's rainfall that you don't see in the river. Therefore, effective rainfall is gross rainfall depurated by water losses. In this case, here you have effective rainfall. And I realized that probably I did not emphasize enough this concept. So, it's not just enough, you know, to apply this integral to compute river discharge. You have also to estimate P, which is net or effective rainfall. You need an infiltration model to do so. I'm not going into the details of infiltration model. I take for assumed that you know about infiltration models, because these are basic concepts that are studied in the hydrology courses. In advanced hydrology, I assume that you already know. It's not a big deal. If you don't have clear the concepts, it's not a problem, because I'm not asking you infiltration model during my exam, and if you want to refresh for your personal interest, just look at your notes or Google it, infiltration models, and you find everything you need. Okay, good. Please remember that the basic concept here is conservation of mass and conservation of energy. So the basic concept here is Reynolds transport theorem, which allows you to derive these conservation laws. Okay, because I think it's important. These are empirical models in a way. So one may study these models even forgetting, even not mentioning conservation of mass and energy. But I think that it's important in an advanced course that we always keep in mind the physical meaning, because if you want to make the models more complex, then we have to introduce additional equation, and the principles are always conservation of mass, energy, maybe momentum. Okay. Now let me see if I forgot something. I would say no. And now let me slowly introduce a more complicated model, because I want to show you how we can get a better representation of processes, how we can better define the rainfall runoff transformation. So I just want to mention one more model in a quantitative form, meaning that, I'm sorry again, I will have to write down on the blackboard mathematical relationship, and this is the last rainfall runoff model that I will define in detail, so please be patient even today. And then I will talk to you about other models, but in a descriptive form, not in a quantitative way. So, as I said, I want to slowly move towards a more complicated model, and let me start by putting in evidence the limits of the linear reservoir, because the more complicated model that I want to introduce is a kind of generalization of the linear reservoir method. And I think it's non-linear, the model that I'm introducing, and I think it can be considered a generalization of the linear reservoir. And so let me put in evidence some limitation of the linear reservoir. The linear reservoir does not impose any limit to the amount of water that is stored in the basin, in the catchment. So the quantity WT that we forgot about because we eliminated the quantity W, we just combined the two equations in order to eliminate W, because we are not interested in computing W. But anyway, W is directly related to QT, because we remember W was exactly W is equal to QT times K. K is the dimension of a time. So, W, as I said, is not limited. There is no upper limit. And this is physically not reasonable. We can't put any upper limit, because if we put a limit, the model would be nonlinear. Because if we put an upper limit to W, we have to change the model, of course. What happens when W is reached? There is a threshold, you know. You could say, for instance, it would be quite easy to update the scheme, the conceptual scheme. The conceptual scheme that I depicted yesterday is given by a tank where we have a water content W depending on time, and we have an outflow from the bottom, and we have some net rainfall entering in. So, if we put a limitation to W, let's say that we put a limit which is W max, we could say that once that the tank is full, we get an overflow from the tank. So we could call this like Q prime T. And we could compute the total discharge by summing the two components. And the second one occurs only when the tank is full. We could say this. Conceptually, it's very simple. And it's also quite reasonable. We can assume that when the catchment is full, then every rain that falls over the catchment turns into runoff, into river discharge. It's reasonable. But of course, we need to change the model. The mathematical relationship would not be this one anymore. It would be different and would be non-linear, because you would get a threshold, you would get a threshold. When the tank is full, the rainfall runoff transformation changes its shape. So getting a threshold effect. And okay, but we could do that. We cannot use the integral anymore, but we can use numerical integration very easily. We will see an example during our exercises. But what we note, if you use this scheme, is that this threshold is too sudden, meaning that you get an effect on the hydrograph that is not realistic. If you look at the resulting hydrograph, which is, again, the hydrograph is a graph of QT versus time. If you look at the hydrograph, you see a sudden increase of the discharge when the reservoir gets full, which is not realistic. This is what we note. And we will carry out an exercise on this. This is not realistic. In fact, if you think at a catchment, it's not realistic that there is a time instant where the catchment gets full. This is not realistic. What happens in a catchment is different. It's not reasonable that you, at a certain time, you get the catchment that is full of water, not storing water anymore. what happens actually? What happens in reality? If you look at a catchment from above, and there is a river network in it, what happens if it rains is that at the beginning of the event, typically, the catchment absorbs all the waters, all the rained water, meaning that all the rainfall infiltrates in the catchment. This is what happened at the beginning. And if it continues raining, then in some areas of the catchment you get indeed saturation, meaning that these areas cannot absorb water anymore. And typically these areas are the areas close to the river network. Why this? Because you have a concentration of water, of course, close to the river network. You have the water converging there from the hill slopes, and you get saturation. So you get this area here which saturates and cannot store water anymore. So in this area, indeed, all the water that rains turns into runoff directly. Maybe flowing just a few centimeters below the ground, not directly over the ground, but in any case it doesn't infiltrate anymore. So you get indeed saturation, but this saturation is gradual. You don't get a full saturation of the whole catchment at the same time. Of course, this saturated area increases in extension if it continues raining, and then after a certain time you could get the catchment that is saturated, completely saturated. This is possible. Typical during flood event, you get a condition of almost saturation, almost complete saturation. But you don't get saturation at the same time over the catchment, complete saturation at the same time. It's a gradual process. And therefore you don't see in nature a sudden step in the hydrograph, because you see the hydrograph that increases gradually, because of course saturation increases, and then you see the hydrograph increasing. The moral of the story is that this scheme, although reasonable, is not reliable. Therefore, it's not advisable in a linear reservoir model to introduce this kind of threshold, because the effect is not realistic. But at the same time, it's not completely reasonable that you don't put any limit in the linear reservoir to the value of W, because if you don't put any limit, it means that you never reach saturation. Even if you get a rainfall that is continuing for days, you never reach saturation according to the linear reservoir, because the stored volume of water can increase until infinity. So what would be the solution? Let's try to introduce a model that allows us to take into account this process, this kind of process of partial saturation, increasing saturation. Let's introduce a model that allows us to take this concept into account. And these models, it's a class of models indeed. I will provide an example that refers to one specific model, but there is a class of models, like there is the class of the linear models, there is a class of models that can reproduce this effect. Sorry. And these are called variable contributing area models. At terminology is self-explaining, you know. Variable contributing area, because it varies. The contributing area, or better to say the saturated area, changes in time. And this class of models is based on two assumptions, or on some assumptions, but let me put in evidence two basic assumptions. The first one is that you use gross rainfall here. I want to make it clear. You use gross rainfall here, and we will see how the model takes into account the fact that there is some rainfall that is lost due to evaporation, etc. And the second assumption yes, I didn't remember the assumption. The second assumption is that the transformation of rainfall into runoff is carried out accordingly to these mechanisms. First of all, until saturation, you don't get any contribution to river discharge, meaning that all rainfall infiltrates. So, when it starts raining, rain that falls over areas in the catchment that are not saturated is completely stored in the catchment. It's a different mechanisms with respect to the linear reservoir, and because in the linear reservoir at the beginning of the event, you have, soon after the beginning of the event, you have a discharge from the bottom. In this case, you may have discharge at the outlet if there are impervious areas, because of course in impervious areas the saturation, the water storage capacity is zero. There is no possibility for the soil to store water. But if you don't have any impervious area, you don't see any water. It starts raining, and you don't see any water in the river until you get saturation somewhere. So the concept is that until saturation, you don't get any river discharge. Keep in mind that there might be, I repeat the concept, there might be impervious areas. Impervious areas are by definition saturated at the beginning of the event because they can't store water. So you might see some discharge at the beginning of the event, but only if you have impervious areas. Okay, so no discharge until saturation. Of course, when you get some areas that are saturated, like in this case, you get a discharge from the contributing area, which is variable in time. Okay? Now, what kind of scheme can we use to describe this process? There is a possibility that comes immediately in our minds, which is using a spatially distributed model. I mentioned to you that there is a class of models that are based on the concept of subdividing the catchment area in sub-catchments. Therefore, if we wanted to describe this process where some areas are saturated and others not, we can use this strategy. Let me draw again the scheme of the catchment. So if we have this catchment here, the strategy could be, okay, let's divide the catchment in sub-catchments, and for instance, one can use a grid, a regular grid, or you can use subcatchments. Let me take the example of a regular grid. And you get these subcatchments. And let's put here a linear reservoir in each area, which its own value of W max. And then we can put another linear reservoir here, a linear reservoir in each subunit, again with the value of W max. Let's call this one W max 1 and this one W max 2, because they can be different. So the strategy could be, let me use a series of linear reservoirs, each area with its own reservoir. So you get a combination of linear reservoirs. This could be a strategy. If you want to take into account the fact that the catchment doesn't saturate completely at the same time, you can then subdivide the catchment in sub-areas, each one characterized by its own linear reservoir. In this case, you get saturation at different times. And you don't see the sudden step in the hydrograph anymore. This is a possible strategy. Take into account that if you use this scheme, you need a sub-model, a sub-Rainfall-Runoff model, to describe the propagation of the flow from each linear reservoir to the outlet, because you are interested in modeling the river flow at the outlet. So you need a sub-model which is called a flood or flow routing model to transform individual contribution to the outlet. But this is possible. Indeed, it is done. Many rainfall runoff models use